Alright, so today I'm going to be explaining another important paper with the title Graph-Guided Diffusion, Unified Guidance for Conditional Graph Generation. You know, this guidance is really important in diffusion. And this paper is just about graph generation, and we can condition on some properties. And so this paper in 2025. So let's see what is the motivation of this paper. Diffusion models have emerged as powerful generative models for graph generation, yet their use for conditional graph generation remains a fundamental challenge. In particular, guiding diffusion models on graphs under arbitrary reward signals is difficult. Gradient-based methods, while powerful, are often unsuitable due to discrete and combinatorial nature of graphs and non-differentiable rewards after complicated gradient-based guidance. So they propose this GGDiff, graph-guided diffusion, a novel guidance framework that interprets conditional diffusion on graphs. They see it as a stochastic control problem to address this challenge. So it unifies multiple guidance strategies, including gradient-based guidance, when we have differentiable rewards, and control-based guidance, using control signals from forward reward evaluations and zero-order approximations, bridging gradient-based and gradient-free optimization. So this plug-and-play framework enables zero-shot guidance for pre-trained diffusion models under both differentiable and non-differentiable reward function, because your reward function can be non-differentiable. So our formulation balances computational efficiency, reward alignment, sample quality, enabling practical conditional generation across diverse reward types. So what they did, they work on various tasks like having constraints on graph motifs, fairness, and also link prediction. So here you see illustration of GGDiff, a method that guides the generation of graphs to satisfy a set of constraints. For example, here the constraint is fairness. This is fair, this is not fair, this is unfair. So the guidance, this U of t here in this picture, you see, is a local direction obtained via SOC and approximated using ZO techniques like the multi-point estimate. So it unifies various existing guidance methods. We skip this background that you need. So this controlled the generation of graphs with continuous diffusion models. A plethora of work proposed solution of problem 1 in the context of inverse problems in images. In general, these works assume a differentiable reward, the likelihood associated with a noise in measurement, which allows us to compute the conditional score at noise level t obtained via Bayes' rule. And this naturally allows us to incorporate the diffusion model as the prior. However, the score associated to the likelihood term is intractable. To circumvent this, different works propose to use Gaussian approximation centered at MMSED noiser, which can be computed using 2ED formula. So in the context of graph, digress and LGD incorporates a guidance via a learned model. They use similar to classifier free guidance. If you remember digress, I've explained it in one of the videos. If you remember, so it's requiring an extra learnable model. However, this approximation remains largely unexplored in the context of graph inverse problems, mainly because it requires differentiable rewards, which are in general not available for graph generation. So this prodigy, I explained it in a different video, exploit an alternative for controllable graph generation with a non-differentiable constraint. Their core idea, if you remember, it involves an unconditional generation step to produce candidate. So we did this projection operator. I explained this, that at every iteration we need to do this using that KKT condition, if you remember. So while direct projection ensures the sample satisfies the constraint, applied fully at each noise level can disrupt the learned reverse trajectory's smoothness. So Prodigy proposed a partial update. So a little bit of the previous and a little bit of the projection. So we are not doing something extreme. So this gamma T here, it balances these two worlds. These two balances constraints adherence with original diffusion path. So what is this SOC approach? The goal of our method is to steer a pre-trained diffusion model to sample from posterior distribution. Importantly, we seek an algorithm that can handle general reward functions, even non-differentiable ones. To tackle this, we propose to leverage SOC. In particular, given an uncontrolled diffusion process Q, we define a controlled one. This Q controlled. So the goal is to design this control. I mean, in control theory in electrical engineering, because I had my BS was in electrical engineering, we use U for control. For example, I remember if we have a linear system, AX plus BU, so everything is linear, and then we have an output, for example, CX plus D. DU. So U here is control, also implicitly is also related. So here is again, the notation is the same. We are controlling U. For example, here in the control system, U is control, X is the state of the dynamical system. Of course, this is a linear system. In general, we have this dynamical system, this nonlinear system. U is the input, X is the state, and F is a nonlinearity. So this is very general. It can produce chaos as well, depending on the nonlinearity. So here they use the same. They use stochastic. You know, in stochastic control, we use f of xu plus another term, dw. W is just a Brownian motion. It completely looks like the forward of the diffusion. So you see all of these ideas are related. Because in nonlinear control, we can use Hamilton-Jacobi-Bellman equation. If you have an objective, if you have a functional, we can derive what U is good to reduce the functional. But here they did something different. The goal is to design a control to modify trajectory of control process such that the generated samples belong to target distribution. So we solve this optimization problem. The terminal cost in 3 represents a desired constraint for final state, quantified by the reward R. So when we say reward, this reward is here. We are minimizing the distance to the reward, if you see. Because this looks like energy of a input, Frobenius norm. And now the transit term is a regularization term that penalizes large deviation from uncontrolled process by promoting the energy of the controller. In equation 2, we want the energy of the controller in this one to be small. So the solution of this equation 3 is just, we know it. We know from Feynman-Koch formula that in optimal control, we just use the solution of that. And the solution is obtained as a solution of linear version of. So this is, as I said, HJB. This is a solution. This is a linear version of HJB because HJB is more general, and so you know the solution. Isn't it interesting that we are minimizing this expectation of this functional, and of course subject to these constraints. So although expression of optimal control drive for Feynman formula is theoretically exact, its direct computation is often intractable. So we resort to the greedy approximation strategy. This approach simplifies the problem by approximating the complex gradient of log expectation using primarily the current state information and a one-step estimate of the clean sample. Such an approximation implies that the control decision at time t does not fully account for the entire future trajectory, potentially leading to suboptimal choices, especially in the early stages of the reverse diffusion process. However, the impact of such approximation errors may often diminish as time goes to zero. So this differentiable rewards, first we start with differentiable rewards. When the reward function R is differentiable, we can derive a tractable approximation of the optimal control. The primary challenge lies in evaluating the gradient of the log expectation. So we use the 2D formula to compute the MMS in denoiser. So we approximate the conditional expectation like this. You approximate it. So it's like e to the minus reward. And so if you substitute into equation 4, if you substitute the equation, because we have approximate that, so if we substitute into equation 4, it leads to this U star. So this final expression provides a tractable, greedy approximation for the optimal control. And the control term now directly involves the gradient of the reward function. So interesting. Everything I've learned is related to each other. Everything. Nonlinear control, diffusion, Feynman-Koch, everything is related to each other. Even financial mathematics, everything that we derive for Brownian motion, everything is related to each other. And the second part, they talk about non-differentiable rewards, because sometimes we have a control graph generation, the reward is non-differentiable. Like the previous 3 videos, we had a non-differentiable reward function. Of course, we didn't use the word reward, but now you understand all of these you can think about as a reward function. So we seek to find a direction like a control input, using an approach inspired by gradient-free optimization. So here the summation is a perturbed version of G hat. Instead of G hat, we use a perturbed version of that. So it's generated the graph with reference model at time t before applying the guidance. Following the control, then we have this control direction. So mu is a smoothing parameter. So to find U star, we define a general ZO estimator for the gradient of the reward. So it can be the estimator can have different forms, like 1-point gradient estimator, which samples a single perturbation direction and evaluates the reward by perturbing an unconditional generated graph with a single direction. It can be best of n direction. This is a greedy zero order. And instead of sampling a single direction, this method samples n candidate directions. You can be a multi-point gradient estimator, like an average random search. So the input of this algorithm is just mu and sigma and t and epsilon. So we compute the graph and the input control, and here we compute this g hat, then we approximate, we set the control to be the argmax, or we approximate it, instead of argmax we use just the gradient. And finally we go in the direction of the control. I mean, we move the graph in a direction of the control by g plus ku in this direction. It's like a directional derivative. Think about it. So we have this task. We want to evaluate to generate graph consistent with partial observed adjacent. Sometimes you have a partially observed adjacency matrices and you want to generate graph. So we assume 50% of entries of adjacent matrix are observed and should be maintained in the generated graph. So you can see in the appendix some more details.